Area B, roll number 127. Have you ever wondered how complex data structures are handled efficiently in Java? So let's dive into the world of n-dimensional arrays and matrix manipulation. Before knowing n-dimensional arrays, we have to know a small concept called temporal manipulation. Let's discuss that first.
So let's discuss temporal manipulation and persistence in data structure. Temporal manipulation and persistence in data structures is an interesting concept that relates to how we can manage and keep track of data over time, often allowing us to go back to previous states or even travel through time in a computational sense. Let's break this down in a very intuitive way. Temporal manipulation. Think of temporal manipulation in data structures like keeping a record of every change that has ever happened to your data so you can access or even revert to any point in time. Imagine your data structure is a diary where you can write down something new every day. Temporal manipulation allows you to read any entry from any past data, look at what your diary looked like at any specific day in history, and potentially undo mistakes by returning to an earlier version of your diary. So now let's discuss why is temporal manipulation important. First is historical analysis. Temporal manipulation refers to the ability to manage and analyze data across time. It enables tracking how data changes and evolves over time. Examples are seeing how customer preferences changes over seasons, monitoring performance metrics across different periods, and identifying long-term trends in business data. Next is error recovery. It works like a sophisticated backup system. Some of the key features are it preserves different states of data at various points in time, allows rolling back to any previous state if error occurs, and maintains data integrity during recovery process. Next is audit trails. It creates a detailed record of all data changes. Some of the important aspects are track who made changes, record when changes were made, and documents what was changed, and essential for regulatory compliance. Next is predictive modeling. Leverages historical data for future insights. Benefits are it improves accuracy of forecasting models and helps identifying recurring patterns. It enables better decision making based on past trends. So now let's discuss applications of temporal manipulation. Primary use, first is financial analysis. Primary use are it's used in stock market analysis, market trend analysis, performance tracking, and historical analysis. Its key benefits are it enables technical analysis, helps in risk assessment, it supports portfolio optimization, and facilitates backtesting of trading strategies. Next is healthcare. Some of the primary applications in healthcare are patient monitoring, disease progression, treatment effectiveness, and health trends. Key benefits are it improves patient care through data-driven decisions, it enables early detection of health issues, and helps evaluate treatment efficiency. Next is version control systems. Some of the primary functions are code management, collaboration support, project evaluation, and change tracking. Its key benefits are it facilitates team collaboration, maintains code integrity, enables bug tracking and fixing. It supports feature development and rollback. Now let's discuss ND arrays. Introduction to ND arrays. N-dimensional arrays are a powerful data structure used to represent and manipulate data in multiple dimensions, beyond the simple row-column format of traditional 2D arrays. In programming languages like Java, ND arrays are particularly useful for complex data modeling in areas like scientific computing, machine learning, image processing, and physics simulations. Let's delve deeper into theoretical concepts around ND arrays, their applications, and how they are implemented in Java. So, what an ND array is? An ND array is a generalization of arrays into multiple dimensions, extending the concept of 1D array and 2D array into higher dimensions. In 2D array, you have rows and columns, but in 3D array, you add another layer like a stack of matrices. In 4D array, there is yet another level and so on. Each dimension represents a distinct attribute or axis of the data. For instance, in image processing, a 3D array could represent width, height, and color channels like RGB. So, let's discuss temporal manipulation in ND arrays. First is time as a dimension. Time is treated as an additional axis in the ND array. Example, 3D array becomes 4D with time. Axes are X, Y, Z, and T. It enables seamless integration of temporal data. Next is slicing and dicing. Some of the key features are it extracts data across specific time periods, analyzes temporal patterns at different spatial points, and performs cross-sectional analysis. Next is efficient updates. Only modified data gets duplicated and unchanged data shares memory with original. It preserves history while optimizing memory uses. The key benefits are memory efficiency, performance, and analyzing capabilities. Next is applications of NDRS. First is scientific computing, representing and manipulating matrices, tensors, and complex multidimensional data sets. It is also used in machine learning and deep learning by representing tensors of weights, biases, and inputs or outputs in neural network. Next is image and signal processing, storing color images as 3D arrays like height with color channels or even higher dimensional for videos. So ND arrays are critical in various domains due to their availability to efficiently organize data across multiple dimensions. So let's see the challenges with ND arrays in Java. Java does not natively support complex ND array operations the way Python's NumPy library does. So implementing operations on ND arrays in Java requires more manual setup and handling. Java's arrays are fixed in size once defined, and they are often used in nested form. This makes operations like reshaping, slicing, and broadcasting more complex to implement directly in Java without additional libraries. First is memory management. Java stores multi-dimensional arrays as arrays of arrays. Memory allocation is contiguous for each subarray but not for the entire structure. Each dimension adds another layer of reference in direction. This can lead to higher memory overhead due to multiple object headers, memory fragmentation, and increased garbage collection pressure. Next is indexing and access. For an n-dimensional array, accessing an element requires n-index operations. Cache performance can degrade with higher dimensions due to non-contiguous memory location. The time complexity for index calculation, where n is the number of dimensions, is order of n. Visualization and debugging. Cognitive complexity increases exponentially with dimensions. Mathematical representation. Tensor notation becomes necessary. Let's discuss some key operations on ND arrays. First is initialization and assignment. ND arrays can be initialized manually by specifying values or programmatically by assigning values through nested loops. Next is access and update. Elements in array ND arrays can be accessed and updated by specifying indices at each dimension. Iteration. Nested loops are generally used to traverse each dimension of an ND array. Reshaping and flattening. Reshaping changes the shape of an ND array without changing its data, whereas flattening converts an ND array into 1D array. It's also used in matrix operations. Operations like matrix addition, subtraction, multiplication, and transposition are common for 2D arrays. Slicing and subarrays. In more advanced implementation, slicing allows selecting specific selections of an ND array. Java requires custom methods or libraries to achieve slicing. Let's see benefits and limitations of ND array in Java. Going to the benefits, first is efficient data representation. Advantages are compact storage for complex data structures, organized management of multidimensional data, memory efficient for large data sets. Next is expressive power. Its capabilities are versatile data modeling for image processing, scientific computing, machine learning, time series analysis. Next is performance optimization. Its key features are hardware acceleration support like specialized libraries like ND4J, JBLAS, etc. Next, let's see limitations of ND arrays in Java. First is memory footprint. Its key issues are high memory consumption for large arrays, memory allocation challenges, garbage collection pressure, complexity. Main challenges are it's difficult to visualize high dimensional data, complex indexing operations, error-prone array manipulations, and it's hard to debug. Next is lack of native support. Its limitations are no built-in ND array class in Java, need for eternal libraries, limited standard library support, custom implementation requirements. These are the performance considerations for ND arrays.
So our next concept is matrix manipulation in Java. Matrices are fundamental mathematical constructs that consist of arrays of numbers arranged in rows and columns. Each element in a matrix represents data or a relationship within a structured format, making matrices highly versatile and powerful tools across many domains of computer science. Here's an explanation of why matrices are indispensable, particularly in fields like linear algebra, image processing, and data analysis. First of all, what is a matrix? A matrix is defined as a rectangular array of numbers, symbols, or expressions organized in rows and columns. This arrangement allows for structured data representation, which is foundational in various fields of mathematics and computer science. Matrix representation. Matrices are typically represented with uppercase letters like A, B, or M. Individual elements within a matrix are referred by their position using indices that specify the row and column of each element. This systematic referencing allows for each access and manipulation of matrix data. Next is matrix dimensions. The dimensions of a matrix are determined by its number of rows and columns, usually expressed in the form of rows into columns. Example 3 cross 2. It has three rows and two columns. Dimensions are crucial for understanding the structure and compatibility of matrices for various operations such as addition, multiplication, and transformation. Matrix operations in Java. Addition and subtraction. These are element wise operations, meaning each element in one matrix is added to or subtracted from other corresponding element in another matrix. This operation requires both matrices to have the same dimensions to align corresponding elements. In Java, implementing this would involve looping through each element in the matrices and performing the addition or subtraction. Next is scalar multiplication. Scalar multiplication involves multiplying every element of a matrix by a single value. This operation scales all the elements in the matrix uniformly by the scalar value. In Java, this would involve iterating through each element in the matrix and multiplying it by the scalar value. Next is transpose. The transpose of a matrix is obtained by swapping its rows and columns. This means that the element at position ij in the original matrix moves to the position ji in the transposed matrix. Transposition is useful in various applications such as simplifying matrix multiplication or working with row and column vectors. In Java, creating a transpose involves creating a new matrix where each element is assigned from the original matrix with rows and columns interchanged. Each of these operations form a foundational part of matrix manipulation, enabling developers to perform transformation, scaling, and data rearrangements that are essential in applications like data analysis, graphics, and scientific computing. Next is matrix multiplication. First, full dimensions. Matrix multiplication is defined when the number of columns in the first matrix is equal to the number of rows in the second matrix. What's the process? The resulting matrix is found by multiplying each row of the first matrix with each column of the second matrix. Applications. Matrix multiplication is essential for tasks like image transformation, computer graphics, and data analysis. First, next, let's discuss application and use cases. Image processing. First is image transformation. Matrices are used to rotate, scale, shear, and translate images. This is achieved by multiplying the matrix representing the transformation with the matrix representing the image pixels. Filtering. Image filters like blurring or sharpening can be implemented using matrix operations. Each pixel's value is adjusted based on a filter kernel, which is represented as a matrix. Next is feature extraction. Matrices are used in techniques like principal component analysis (PCA) to extract significant features from images, which are used for tasks like face recognition and object detection. Next, second is data analysis. It's used in linear algebra foundation. Matrices are the bedrock of linear algebra, which is fundamental to understanding and manipulating data. Operations like matrix multiplication, inversion, and decomposition are essential tools for data analysis. Statistical modeling. Matrices are used to represent and analyze data in statistical models, including regression analysis, factor analysis, and time series and analysis. Next is machine learning. Matrices are used extensively in machine learning algorithms. They form the basis of neural networks, support vector machines, and many other algorithms, enabling data transformations, weight updates, and predictions. The last one is graph theory. Relationship representation. Matrices can represent connections and relationships in graphs, which are networks of nodes and edges. The adjacency matrix, for example, indicates which nodes are directly connected. Next is network analysis. Matrix operations are used to analyze graph properties like centrality, connectivity, and shortest path. This is useful for understanding social networks and transportation systems and communication networks. Now, let's see code on implementing temporal data structures using standard implementation in ND array. Import java.util.arrays. It imports the arrays utility class from Java standard library. Here, we are declaring a new class named temporal array. Next, private int values. An array that holds integer values added to the temporal array. Next, private long timestamps. It is an array to store timestamps associated with each integer value in values. Timestamps are stored as long values. Private int size. It tracks the current number of elements in the array. Private int capacity. It holds the maximum capacity for the temporal array. Next, it's constructor for initializing a temporal array object with a specified capacity. This dot capacity is equals to capacity. It sets the capacity field to the field passed as a parameter. This dot values is equals to new int of capacity. It initializes the values array with the specified capacity. This dot timestamps is equals to new long of capacity initializes the timestamps array with a specified capacity. This dot size is equals to 0 initializes the size field to 0, indicating that the array is initially empty. Next, public void add of value. It first checks if the current size is equals to capacity. If it is, it prints a message indicating that the array is full and returns without adding the value. You can see in this line. If there is a space, it stores the value at the current size index in the value array and it records the timestamp at the same index in the timestamps array. Finally, it increments the size to reflect the addition of new element. Next, let's check public in get valued time. Here we are using for loop. It iterates through the timestamps array from index 0 to size minus 1. If timestamps of I is equals to timestamp, that is, if it checks if the timestamp at index I matches the timestamp parameter, it returns the corresponding value from values if a match is found. Otherwise, it throws an exception if the specified timestamp is not found, signaling an invalid request. Next, public void print array. Its method to print all values and the corresponding timestamp. Here, for loop iterates through the array up to the current size. Then it prints value and its corresponding timestamp in formatted string. Next, now comes the main function, the main entry point of the Java application. Temporal, here we are creating an object for temporal array and we are adding elements. First, we are adding 5, then 10, and then 15 to the array, each associated with the current timestamp. Here now this prints the array, temporal array, and it prints value at timestamp and the timestamp. So now let's execute this code.
So here is the output of the code. I hope you all understood about ND arrays and matrix manipulation along with the code. Thank you for watching.